Recording in progress.
Hello everyone, how are you? Good, let's do this. Okay, well happy Friday. I guess it's already Friday and it's also, we're getting close to halfway through the semester. My understanding is that next Friday is the day off, is that right? I think so. So that's scary. That means it's getting close to the end. Also, I guess the other way I know it's getting close to the end is it's getting warm enough to wear short sleeve shirts. Although that seems to be also correlated with climate change, which is maybe not a good thing. Anyway, so we're going to continue talking about interesting ways that we can go about trying to solve recurrences. Although I'm going to take a little step, a little bit afield, and the first thing we're going to talk about is going to look a little bit different. Okay? So this is just a super cool fact that I want to talk about. Does anyone know what happens if you take 1 divided by 89? Well, I guess I need a calculator for that. Let's go and get a calculator. This is my nearest calculator. 1 divided by 89. I wonder if I'll be able to get enough digits. Just a second. Come on. My phone is too slow. Let's go. So 1 divided by 89. Oh, okay, I found it. So let me tell you what it is as a decimal. It's 0.11235. Isn't this awesome? 0.11235. No, you ruined it already, Chris. What did you say? Oh, the next one's a 9. Oh, okay. I'm sorry. So it's not any good. It's 5955. And then what is that? 06. All right. So we were all excited for a moment that it might be something like Fibonacci numbers, but it's not. It's 11235. And what did you really want? You really wanted 8, didn't you? That would have made us happy. Okay, suppose I got 8. What would I want after 8? 13. 1 plus 8 is 9. That's satisfying. What do I want after 13? 8 plus 13 is 21. Ooh. 3 plus 2 is 5. It works! This is amazing! So you see, there really was something going on here after all. It's actually just Fibonacci's, but you had to mash numbers together. Is everyone with me? Do you all believe me at this point? I've done the small cases. I've done like up to 7 or something, so it must be true. Well, what's next? 13 plus 21 is 34. Uh-oh. All right, it broke. I mean, it's too good to be true, right? So there's no way this thing could be true. Because you see, the problem is 1 plus 3 is not 5. Actually, it gets even worse. What's after 34? 21 plus 34 is 55. 4 plus 5 is not 0 either. So it's like totally and utterly broken. Anyone know what's after 55? 89. Wait a second. You know what's going to happen when you add the 5 and the 8? When you add the 5 and the 8, there's going to be a carry. And then now that carry, the 1, the 4, and the 5, that's 10. Oh, look at that. That matches. And furthermore, 10 gives me another carry. Bam! It all works. Okay. So at this point, hopefully you believe me that something very interesting is going on with this 1 over 89. And I mean, the reason, by the way, has nothing to do with the fact that that is 89, which is also a Fibonacci number. That is a pure coincidence. 1 over a Fibonacci number does not just give you this Fibonacci decimal. But this is super cool. And it actually works in the sense that if you just keep going and going and going, and you just like always carry in the right way, you're actually going to recover this decimal on top, which is unbelievable. The first time I learned this, by the way, was when I was teaching a Putnam class at CMU. And one of the students said, hey, didn't you know there's this like 1 over 89 thing you can use? And I was like, what do you mean this 1 over 89 thing? And they did it, and it was like this. And I was like, no, this can't possibly be true. But okay, so why is this true? Let's go and attempt to prove this, okay? But what does prove this mean? Prove this means we need to write down some formula about Fibonacci's for which the answer comes out to 1 over 89. Let's remember, so of course now you see it's related to Fibonacci's as we should have expected. So Fibonacci's, remember we start with f0 is equal to 0, f1 is equal to 1, f2 is equal to 2, and so on. That's the Fibonacci's. Okay? So I guess a question I have is, can anyone try to rewrite the right-hand side? What's the right-hand side? In terms of f's. We might have to write things in terms of f's, and how can I write all of this? It's an infinite sum, by the way, about f's. Anyone have any ideas? So let's get some different people here. Andrew.
You could like multiply each Fibonacci number by like a corresponding power of 10.
Okay, I'll do a divide just because it's easier for me to write, but it's the same as what you said. Can you help me out? So it's f0 divided by a power of 10 plus f1 divided by a power of 10. Okay, what are the powers of 10 that I should use?
So the first one would be just 10, and then you would want 10 squared, and then you'd keep going.
Over 10 cubed, and so on. Okay, so I think my real goal is to attempt to prove that this sum of Fibonacci's over powers of 10s, I'd love to prove that that's 1 over 89. Do I have any hope of doing this? Let's try, okay? So I'm going to rewrite onto the next screen just this simple sum of f0 over 10 to the 1 plus f something over 10 to the next thing is what I'm going to write, okay? I just need more space, so I do it on the next screen. Your goal is to show f0 over 10 to the 1 plus f1 over 10 squared plus f2 over 10 cubed plus all the way is equal to 1 over 89. Now, how could I do this? Well, I don't know much about Fibonacci's. I know that the small ones, I know what they are, but I don't really know what the big ones are. Like, and I can't tell you what is f50 million. I mean, I could if I tried very hard, maybe, with this nice formula we had found. But what I do know about Fibonacci's is I can make them out of the previous ones. Actually, there was a funny joke I saw online a few weeks ago, which said, what was it? It was a cafeteria. It was like some school cafeteria, and it said that today's menu, the special soup of the day, is called Fibonacci soup. What we did is we took yesterday's soup's leftovers and the day before yesterday's soup's leftovers, and we mixed them together, and that's called Fibonacci soup. I thought that was quite funny. And actually, where I went to college, sometimes when you went to eat dinner, you'd be like, what did the chef just make? It looks like what was left over from yesterday, remixed. Anyway, that's called the fried rice. Okay, let's continue. So now if you go on here, nothing against fried rice, by the way. Fried rice is a fantastic dish. Okay, continuing this thing. Let's go and say suppose that this thing is called x. Okay, let's just let the left hand side be called x. Okay, do I want to use? Yeah, why not? Let's use x for now. Big capital X equals this sum. That sum. I just don't want to write it again. It's that sum. Okay. But now I want to go and use Yeah, I want to go and use some idea of like what to do. And what should we do? Advait, you had your hand up. Did you want to do something?
Yeah, so from F2 onwards, what if we use the recurrence and split it?
All right, let's try that. So
And
what
then
I'm going to do...
see if we can, I don't know, recover some weird version of X.
Yes. So again, as you can see, actually, I was chatting with somebody about how I teach my classes and about notation. That guy was called Black Pen, Red Pen. I don't know if any of you guys watch his thing. So we did some random live stream earlier this week on Tuesday. And what I explained is I just don't do notation. I just write dot, dot, dots and hunt for patterns, preferably after 7 terms. And so if you do this, then you can just like see stuff, right? So let's split things apart. What's F2? Well, I can break F2. F2 breaks into F1 plus F0, just like that Fibonacci soup thing. So it's going to be an F0 over, 10 cubed. I'm going to use columns to do this. And the second one is plus F1 over 10 cubed. Okay, and the next thing I will use F1 over 10 to the fourth. And the second column, I'll write plus F2 over 10 to the fourth. And I'm going to pause here just to take stock of what I've written because I want it all to make sense. So what have I actually achieved? I just went and, there's dot, 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 more stuff is being added, but I just copied the first two because I don't know how to take apart the first two Fibonacci's. On the other hand, I have this F2, which I can take apart into F0 plus F1, which is what I did, and I kept the same denominator, which was 10 cubed. The next term would have been F3, which I will take apart into F1 plus F2 over the same denominator. So I've aligned everything like vertically. Is this okay so far? Yeah, and just to get a nice pattern, I'm just going to emphasize the next one is going to be plus F2 over 10 to the power 5, and then it will be plus an F3 over the 10 to the power 5. And we keep going. Okay. Now what? Well, Advait said it would be great if I could recognize some X stuff in there. The thing that's scary is dot, dot, dots. Dot, dot, dots, I don't know what they are, but I know how to add like 3 things together. You just add them. Can anyone see a way to like circle a bunch of stuff here and say, I see X? Braden.
Well, the top row, you can see we have the F0, F1, and F2 in the terms that we have in X, except now we're divided by 10 to the power of 2 additionally.
Yeah, it's like the normal X divided by 10 to the power 2. It's an extra 2 tens, right? Mm-hmm. It's because what happened is I would normally have done X is just F0 over 10 to the 1, and then F1 over 10 to the 10 squared, and then F2 over 10 cubed. And when you write out enough stuff, you just see the pattern. It's like it's just off by 2 factors of 10. So that's X over 10 squared. That actually is very, very exciting because then there's no more dot, dot, dot. I can just be like, forget the dot, dot, dot there. What else? Subhashish. Oh, no. You say that again, what are you going to say?
Oh, I just meant like that's only justified if we know the sum converges. I mean, I think we do because the top is like quadratic and the bottom is exponential. But I was just saying like the dividing and using that in any algebra is justified only if the sum converges.
Yeah. So you actually jumped ahead to a punchline I was going to make in a little bit, which is cool. I'm glad you said that. So what we're going to do in this class is like we don't know what convergence means. so actually what I'm going to say is like I was okay using some ideas from matrices to talk about the previous section. If you want to do everything we're doing in this new section rigorously, you actually need to understand convergence. And that's a class usually not taken until later in a college career. It's usually taught in a class called real analysis or complex analysis. And so what I will do for the rest of this section is we'll just do weird stuff. And we'll be like, yeah, sometimes it converges, sometimes it doesn't, but that's beyond the scope of this class. Okay? And Subhashish, yes, it's not quadratic, it's actually exponential, but the base of the exponential is small enough, that's why it's okay. But in any case, it's all right. We're just going to do like on this level. All right? And that's actually why I went and showed the linear algebra part first, because that part is like absolutely rigorous. Nobody has any questions about dot, dot, dots. We didn't have any. We just had to do like multiplying matrices. Here we have dot, dot, dots, and that's more mathematically sophisticated. How about the second one? Can anyone help me fix the blue stuff? I still have dot, dot, dots here. I would love to be able to rewrite this blue line in something that has X involved. Anyone else? I want to make sure a lot of people are understanding this, because this is what we're doing here is the heart of the next part of the section that we're talking about, just with like some very explicit numbers. It's sort of like x, but not really. Ising.
I'm not sure about this, but it's like x minus like f0 over 10 squared. Like,
Okay, yes. So you said it's x minus, you lost the first term, okay? f0 over 10 to the 1. That's there. We lost that term, but then we need to do more division. Is it
yeah,
okay
like
with
10. Yeah, over 10 squared.
Yeah, here I will actually say, I'm not sure I want 10 squared. I'm looking at this carefully. I'm like, look at the powers I've got. Normally with the x, the f2 divides by 10 cubed. And here my f2 divides by 10 to the 4th. So I only, yeah, it's okay. It's just like it's a pattern thing, right? So it's like I'm only off by one factor of 10, except I also lost the first term. Okay. By the way, what's f0? f0 is 0. Okay, that's very convenient, okay, right? f0 just happens to be 0. This is not what always happens, but in this particular case with Fibonacci's, f0 equals 0 for Fibonacci. Okay, so since f0 equals 0 for Fibonacci, now I have an equation I can write down. X equals, okay? So what I just found out is that x equals x over 10 squared. Oh, let's use the colors. Let's match the colors. All right. So I have x equals yellow. X over 10 squared, I'm just going to call x over 100. And then plus, it's just plain blue x over 10. Wait, what just happened? Oh no, I forgot some terms, because otherwise I got x equals 0. That's really bad. Okay. So there's some terms in front. There's actually some stuff in front. I forgot. I'm going to erase this and write some green. f0 over 10 to the 1, that was 0 over 10, plus f1 is 1 over 100, okay, and then I write the yellow part, plus x over 100, and then I have plus x over 10. Hey, I know how to solve this equation. There's only x, there's no dot dot dots, right? So what happens? How do I do this? Put all the x's on one side. So how much x is on the left side? Well, it's 1 minus 1 over 100 minus 1 over 10 many x's is equal to 1 over 100. Sounds like a good idea to scale up by 100 on both, so multiply both by 100. That's 100 minus 1 minus 10 x equals 1. Look at that, 89x equals 1. So I get that x equals 1 over 89, and it works. So that's cool. So this actually works. All right. So this is very nice. It's actually showing that if I ever were to write something out like this, I could actually go and find this. I could go and find this fraction that is it. Okay. One thing I wanted to say that Subhashish jumped on, which I want to make sure we know, this is slightly wonky math because we replaced some dot 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 stuff. And I'm going to show you something that should make us very worried. Watch, I can prove for you something. Let x, here's something else. Oh, let's call it y. Y equal 1 plus 2 plus 4 plus 8 plus 16 plus dot dot dot. Okay, it's true. And oh, by the way, I can rewrite this in terms of y. Sort of like what we did last time. We were like, that x thing, that was x over 100, right? What's that in terms of y? Y is 1 plus 2 plus 4 plus 8. This is like, what is this? This 2 plus 4 plus 8. What does that have to do with y? Raise hand. Sydney, you already got it. What did you want to say?
Oh, it's just 2 times y.
It's 2y. Obviously, it's 2y. I just doubled everything, right? So what I just found out is that y equals 1 plus 2y, which if I solve, y equals negative 1. So we have just found out that the whole sum is negative 1. Satisfied? Actually, we just had this error. I'm working on this Novid app. So we're doing a lot of programming with our algorithms. We have a lot of C++ code. And late last night, somebody was like, why are we getting all of these numbers in the output, which are like these massive numbers with about this many digits? They're always the same number. And I was like, I have a guess of what they were. And you Google the number. And the number that we kept getting turned out to be 2 to the power 64 minus 1. That's because that's what happens if you have a -1 and you in C++ have -1 and you typecast it to an unsigned 64-bit integer, then -1, actually the way, if you take any computer science classes, the way that you encode -1 in the computer is you have a binary string which is all ones. Anyway, okay, so in a computer, actually, if you take the sum of all of these and you do it in the wrong way, it is actually -1. That's the overflow error you get. Except that we're not computers. The problem of why this broke is because this whole thing was infinity. So actually, there's two solutions to y equals 1 plus 2y. One of the solutions is -1. The other solution is positive infinity. Infinity is also 1 plus 2 infinity, if you could do arithmetic with infinity. Actually, so is negative infinity. That's why actually you can't do arithmetic with infinity. That's why infinity is not a real number, okay? But the bottom line of why the whole thing broke is it's because the thing was infinite. That's why Subhashish said, does it converge or not? So this is just so you need to be careful about convergence. Okay? And that's the reason why this whole subject that we're about to talk about is going to be a little bit weird. It's do things converge or not? And in this class in combinatorics, we're just going to kind of assume you can mess around with things as if they converge. There are theorems later that you can use to go and get that things converge. But I've learned that that's not worth putting into this particular course. The fun part is if you actually get a formula at the end, you can always prove the formula by induction. So in some sense, what we're using is we're coming up with mechanisms to guess formulas we'll be using this to solve recursions. But after you get the formulas, if you wanted to just do it by induction at the end, you could. For this course and for the exams, it's okay to just do all this stuff as if the stuff converges. The ends justify the means. Yes. And in some sense, it's more satisfying than some of those classes which say, here's how you solve the differential equation. You guess the answer. Look, it works! This way, it's you're not really guessing the answer. We're doing educated guesses of if only this stuff converged. And by the way, that's how maybe a few hundred years ago, before mathematicians really had a good understanding of convergence, that's how they were coming up with crazy true formulas with pi squared over 6 is 1 over 1 plus 1 over 4 plus 1 over 9 and 1 over 16 and so on. All right. Well, why did I talk about all this? I just showed this thing to say, yes, so we have to be careful. And what you saw some people murmuring in the chat is yes, you could be careful because it actually does converge, blah, blah, blah. Don't worry about that for this class. Okay? Instead, let's worry about, well, okay, that was nice, but you see, we just had the numbers run together. It would be really nice if we could space out the numbers more. What if instead I could try to find a way to write all of these where I have 2 place values for each spot? So maybe I would want to write not this point 0112359, but I could give some more space. I could go and say point 00, 01, 01, 02, 03, 05, 09, 13. Do you know what I mean? I could give more spaces. You could imagine that would be reasonable. Hey, if I wanted to do that, if I wanted to give myself 2 place values for each thing, what's the only thing I would have to change? If I wanted to find out what is that fraction. If I just want 2 place values, powers of 10, Advait, say again. So what would I change the powers of 10 into?
You double all of them, 10 to the 2 and then 10 to the 4, then 10 to the 6, so on and so forth.
You'd use powers of 100, really. Actually, what I've just talked about is, what if we decided that we were tired of base 10 and we just felt like using base 100? Really, the reason why this is screwing up is because we're writing all our numbers in base 10, and the moment the numbers get bigger than 10, they overflow the place value. That's why you have carrying. And so what I'm going to do next is I'm going to say, hey, what if I just wanted to know in base n? If I wanted the same thing in base n, what would that look like? Okay, so the next question is, we got tired of base 10. We went to a foreign alien planet where they all work in hexadecimal or something like that. And so what is the Fibonacci thing in base n? Well, we just answered that, so I'm just going to write, I saw a question here. Could you adaptively increase the place value? Ooh, okay. Adaptively increasing the place value. Now that gets hard, in that I actually don't think that would be rational. Let me go on that, because that's cool. When you go back to this thing, we just found out that the Fibonacci thing is a rational number. Every rational number is a repeating decimal. isn't it cool that if you just laid out the Fibonacci's like this and you did all the carrying forever, it repeats? Like, what? Do you know what I mean? Like, why would you think that writing down all the Fibonacci's, doing all the carrying, why on earth would it repeat? But it does, because every fraction, if you just do the division out, eventually as you divide out any rational number, it becomes a repeating decimal. So that's just like amazing. Okay. Yeah, and then you got like recursive log 10 addition perhaps, but it's not going to be as nice because I can't just like do this shift. The reason this whole thing worked is I just said, look at that yellow thing. That's just the old thing shifted over by 2 spots, but it wouldn't shift in the same nice way. You'd shift by different amounts of stuff. Wait, is that true? Oh yeah, that's totally true. That's because the problem is that the carrying even screws up. So the reason why this thing worked is because we were able to take the original thing and then break each Fibonacci into 2 parts where they were all divided by the same power of 10 on these 2 pieces. So that's how I could see shifts. But just to, raise hand, Eric.
What if you try like the matrix method from, I guess last week or like this week?
I can't exactly hear you. Could you get closer?
What about using like the matrix method that we were like doing this week?
Ah, the matrix method. So these are related. Like this thing is actually related to the matrix method. But what do you mean by using the matrix method?
Well, okay, if you have like fi times like 10 to the negative I, and then like 10 to the negative I plus 1, fi plus 1, and then you can multiply it by like a matrix, and it would give you like 10 to the negative I plus 1, fi plus 1, and 10 to the negative I plus 2, fi plus 2.
Yes. So what you're saying is that you could actually go and write matrices where the numbers in the matrices. Sorry, are you saying something where you get these kind of vector things, but your vector things are no longer just fn plus 1 and fn, but like fn plus 1 over a power of 10, fn over a power of 10?
Yeah.
Yes, that one will also work. And that's because this thing happens to have all of these nice properties. So that's true. But I'm going to go on with this thread because I want to finish up this piece. I pressed undo. Did anything disappear? Hopefully not. Anyway, let's keep going. So I just want to do this because we had just said this over here. What's the Fibonacci thing on base n? Well, let's do it again fast. So it is we have this x equals. It would have been f0 over n to the power 1. Because remember the base was 10 before. And now the base just happens to be n. Plus f1 over the base squared plus ... If you remember what's happening, I'm just like reviewing this thing fast. Well, what we ended up getting is we got an x over n squared, right? Well, maybe I should do that slowly because this is important enough that we want to. Well, no, we'll see it again. So I'll write this was x over n squared, and then there was this blue thing which was plus. It ended up being just x over n. Is this familiar with people? Like that's what we got, right? This is what we got. This is just like, it was, the reason why one of them is over n squared is because we ended up shifting all of the powers of 10 by 2 more pieces. We got this. Let's put everything together. And what I have here is that, if I move everything together, I get this 1 minus 1 over n squared minus 1 over n times x is equal to, f0 was 0, it's just 1 over n squared. And what I found out is, okay, that's nice. It's like 1 over, if I could do this right, I'm just like simplifying everything now. It's n squared minus n minus 1. That's just algebra. I think this works. Okay, we don't actually need factorials here. I'm looking, factorial base system. So that might be the case. I don't know enough about these things that you're suggesting to be able to give you an answer on the spot. Quite possible. I'm just trying to race the time to get to this punchline because I want to use this to do something else before we finish today's class. But I'm like, okay, here, this will work. And if you put this thing in with n equals 10, that's exactly 1 over 89. And if you wanted to get this Fibonacci decimal thing with every 2 spots, then you just use base 100 and you just put 100 in for n. But this is motivating something else. This is actually saying, look at what we're actually making. We're making some interesting polynomials. Not really polynomials, but over here, well, I don't really mean polynomials. I mean, it's f something and a power of this 10 or a power of this n, whatever that's supposed to do. right? I'm basically saying I've got some f's and I've got some powers of n, but why do we have the n's in the denominator? It's actually better. Oops. Do you get anything interesting for base 5? Possible. But let's go and find out. We're gonna get some power series here, okay? It's like what we were doing is we were basically taking f's, and we were also having some denominators that kept getting bigger and bigger. But if you think about calculus and Taylor series, you usually don't put the x in the bottom. You put it on the same line. So what I want to do here is I actually want to say, hey, let's just define something. Let, I'm going to call it, that looks like a funny f. That looks like an integral sign. It's not an integral sign. F of z, I'm using z as my variable, okay? F of z is just going to be, it's going to be the f0 times z to the 0 plus f1, these are all capital Fibonacci's, z to the 1, plus f2, z squared, plus f3, z cubed, plus so on. What if I did that? This seems like a reasonable thing to do. It looks nice, at least. This looks nice. Okay. Where the digit of the, oh, I see. Yes. So let's keep going here, right? So let's just define this thing. This thing actually has, this has a nice name. This thing is called the generating function of the Fibonacci's. This is called the generating function. Okay, generating function of the Fibonacci sequence, the f sequence. Actually, what does this generating function have to do with that x? There's a way to write x, this x thing, which is the Fibonacci number in base n. There's a way to rewrite this whole thing as something involving f. Something involving f. With this actually as the generating function. Advait.
Well, it looks like you plugged in 1 over n into f and then also divided by an additional factor of n.
Good. Okay, so let's do that slowly. So maybe I shouldn't have written the equal sign is actually that this is equal to the top thing. This is supposed to be an equal sign, right? And what's going on is, you see, if I plug in 1 over n into this generating function, I will get f0 over 1 plus f1 over n to the 1 plus f2 over n squared plus f3 over n cubed, which is awfully like what I wanted for base n, except that what I wanted for base n is divided by another n. So I actually need another 1 over n. Is that okay? I'm basically motivating why this particular generating function is actually useful. Actually, when I first learned about generating functions, people just said, hey, just do this, cool stuff will happen. And then at some point I realized you can actually explain, if somebody wanted to know what does Fibonacci decimal look like in base 572, it's easy. You just put 572 into this thing, and the generating function is actually useful. And so I usually use this 1 over 89 to introduce the whole notion of generating functions so that I don't start by writing this thing, but instead we start by solving a real curiosity, 1 over 89. And then now we discover, hey, this thing might be useful. This kind of a function might be useful. Well, you see, there's a way to get a general form for f. What if we want to solve for this little f? Let's get a form for it. Can I write little f equals something, a function of z, where there's no ... Well, I'll just do the things I've just done. Okay, so let's try to do again what we've just done. That's why this is like practicing the moves quite a few times so we get used to the moves. Well, f of z is equal to, let's leave the first two terms. We don't break those apart because I don't see any use in breaking apart f0 or f1. So I'm going to have the f0 z to the 0 plus f1 z to the 1 plus, now we bust this apart into two things. f2 becomes f0 plus f1. f0, and these are times z squared, right? Plus f1. And then the next thing, f3 breaks into f1 plus f2. So I get f1 z cubed. And here I get f2 z cubed . Now, can anyone help me use generating function stuff to go and replace the ... stuff? I mean, when I say use generating function stuff, I just mean in terms of this like f thing. I'm going to leave the f0 z to the 0 plus leave the f1 z to the 1. And now help me out. What's the green thing? I want to get more people involved if possible. What's the green thing? You can do the green thing in terms of the little f. Yes, Andres.
It should be z squared f of z, right?
Yep, z squared times f of z. Let's put it that way. That was the green thing. How about the blue thing? Can anyone else help me with the blue thing? Preferably new people if possible. Sydney.
You subtract out the first f0 term and then divide by another z.
Okay, let's do this. F of z minus the f0 z to the 0. I'll make a slight correction to what you did, just like times, only because we're doing times here instead of divide, but doesn't matter. It doesn't matter. That's the same idea, right? Because that's how I go and get an extra z factor on everything. Okay, well now let's use the fact that for Fibonacci's, I know what these are. f0 is 0, right? So for Fibonacci's, I happen to know f0 is 0, so those are gone. And I happen to know that f1 is 1. Okay, so this thing here is 1. Let's just write a 1 above it. Okay, so then I can write down an expression for f of z. I know that f of z is equal to just plain z plus z squared f of z plus z f of z. Now, how do you find out an expression just for f of z? I have this nice equation, f of z equals z squared, z plus z squared fz plus z fz. But I want to know what is just plain fz. How would I find out what is just plain fz if I have this kind of an equation? Advit.
You just solve for it. Move all the f of z's away and then divide by whatever you have to.
Yeah, so the important thing is many people aren't used to like solving an equation for f of z as a big blob, which is why I wrote it inside this box. It's an unknown. What I mean is that whatever z happens to be, f of z satisfies this, right? So what if z happened to be, for example, 1/10, because that's something we would care about. 1/10 was this thing for the Fibonacci decimal. And so if z was 1/10, I would get that box equals 1/10 plus 1 over 100 times box plus 1/10 times box, which is actually what we solved last time. Box was x. I'm just emphasizing that box, you can solve for box because all the boxes are the same. So if I continue all the way on the top up here, what I actually have is I have something times box. In fact, it's 1 minus z squared multiplied by this box. And the box is just f of z, okay? F of z, that's box, but that's okay. And that's just equal to z. This is true for all values of z. If z is 1/10, that's true. If z is 1 over 100, did I screw up? I think it's okay. Yeah, this is right. Oh, yeah, okay, yeah. So no matter what is the z, this equation is true because down here, all I did is I just factored it out. The 1 is from the 1 times f of z, and I moved everything to the left-hand side. Okay, well, if that's the case, now I have a formula. F of z is equal to z over 1 minus z squared. Oh, how nice. So now I actually can say if I wanted to know this Fibonacci decimal for base 10, I would just put 1/10 into this thing. I can do it, and I just divide the answer by 10. Very satisfying. But I want to do more than that. I want to now use this fact. This is the Fibonacci generating function, okay? We've just found out the generating function for the Fibonacci numbers. That's the generating function for Fibonacci numbers. Generating function just means I take the coefficients of this big Taylor series thing, and every coefficient is the corresponding Fibonacci, then that's that thing. Now, why would that be useful? That'd be useful because now I can actually look at that thing and try to solve it in a different way. You know what? Taylor series. If I just took the Taylor series of this thing, I would get all of the f's, right? And you know how to take Taylor series? You just take this thing and you differentiate and differentiate and differentiate like 50 million times. Who wants to differentiate this 50 million times? Nobody. Nobody. It's horrible. It's horrible. Like, what do you get? Like, quotient rule and like big old powers are absolutely terrible. No, we are not going to do that. But we're going to do it a slightly different way. So what we're going to say is, hey, if I could find some other way to write this thing down, I could get a formula for the Fibonacci's. I wonder if there's any other way I could write this down. So now let me copy this thing. And I'm going to write this as this z over 1 minus z squared thing. Okay? So that's like this z over 1 minus z squared. Option A is to go and Taylor series it, which we have scrapped. That's going to be horrible. Option B is to look for something else we can do. I'm going to do it one way here, and then in some of the subsequent lectures, we'll find more and more clean ways to deal with this. One way is, I don't like denominators where the biggest power of z has a negative sign. That looks weird. So let's like minus the top and the bottom. Multiply top and bottom by negative. Okay? Minus z over z squared plus z minus 1. Okay. Hey, in calculus, have you ever come across like when you have something which is like a quadratic in the denominator and there's like some particular tool you use, there's a certain area at one point in calculus BC in America, you're going to see things where you're dealing with stuff like this, and usually there's an integral sign or something. What am I getting at? There's an entire area of a thing that you might do if you have like polynomials in the denominator. Raise hand, lots of people. Nick.
Partial fraction decomposition?
Partial fractions. Yes, let's partial fraction decomposition thing. I promise you it'll be fun. So what does partial fraction well, you're not really sure if it'll be fun, do you? But let's just see why this is going to be useful, okay? So let's partial fraction decomposition this thing for fun. Well, it's going to be something over z minus... Oh, I need some letters now. Let's just call them r and s, okay? Z minus r plus something over z minus s. But can anyone tell me, how would I find out what are r and s? I need to put some stuff on top too, right? I need to put some a and some b on top, right? It's going to be this thing. This is partial fractions. But if I want to partial fraction this, how do I find the r and the s, Chris?
I'm just going to go out on a limb here and say that they're phi and little phi.
You're hoping they're going to be phi and little phi, okay? You're actually very close. But why? How would you get them? If you had to partial fraction some nonsense like this, what are you supposed to do?
Oh, they're the solutions to that.
They're the solutions to that. Okay, you got to find the roots. So how do you partial fractions this thing? Let's get the roots of z squared plus z minus 1 equals 0. Quadratic formula tells us negative 1 plus or minus the square root of b squared, okay, minus 4ac, that becomes plus 4 all over 2. I just threw the quadratic formula at it really quick. And I get something not quite exactly what you said, Chris. I get minus 1 plus or minus the square root of 5 over 2. Now, that's not quite the same. It's slightly different. Slightly different. This like the phi and this like what phi minus 1, this golden ratio stuff, that comes from 1 plus the square root of 5. This is a minus 1. But we'll see soon why that is the case. Okay, so I've got these other two. And so I should let one of them be r and one of them be s. Okay? So what I'll say is like let r be minus 1 plus the square root of 5 over 2, and let s be minus 1 minus the square root of 5 over 2. Okay. So now that I've gotten these, what should I do to get the A and the B? Oh, you know what? I think I'm gonna play lazy. I just can't bear to find those. Okay, that'll be too much trouble. There'll be some A and there'll be some B. All right, and we could find them if we wanted to. And if this was actually an AP exam, you would find them out. But they are numbers. A and B you could find out in theory. Okay. Yeah, just like the matrix blob math. That's what we're about to do. A and B are like some blobs, okay? But why is that important? The reason that's important is because, you know, I could maybe find the Taylor series for this A over Z minus R. Maybe that's a nice Taylor series. But here's how to make it even nicer. The way to make that Taylor series even nicer is I'll continue. I'm not going to call it A. And now you're going to see why I'm doing blob math. I would prefer to divide the top and bottom by minus r, a over minus r, over, that's illegible, a over minus r, divided by, what happens if you divide the bottom by minus r? Why is this interesting? What happens if you divide the bottom by minus r? Braden.
You get 1 minus z over r, and I think that might look like a geometric series.
Yes. Yes. So I know how to Taylor series that thing because the top is a blob, okay? That's why I didn't care about the a, because I was like, oh, if I go through all the trouble to find a, oh, sorry, if anyone's wondering, there's going to be a plus sign, okay? We're not done yet. But I didn't bother to calculate the a because actually the a is going to end up divided by a minus r anyway, okay? So it's going to be like blob. It's some number that doesn't depend on n. But it's nice because the bottom is going to look like some geometric series thing. Okay, because the geometric series thing means I'm just going to take like 1 plus z over r plus the square of z over r. You know what I mean? It's like this is the formula for an infinite geometric series. It's 1 plus that ratio plus the ratio squared plus the ratio cubed and so on, of course multiplied by the thing on top, in front. Can someone help me simplify the b term? It's not going to be over minus r. Tell me what to write for the b term. Ising.
Should it be like b over minus s?
B over minus s over, yes.
1 minus z over s.
Yes, 1 minus z over s. Okay, so now this is interesting because this is telling me that if I wanted to write this whole thing out, here's what the answer would look like. The answer would look like, if I split the two, I'm going to say I'm splitting the two because I've got these two things added together. I'll write them as two different rows. I have this thing here, which is the a over minus r. That a looks funny. A over minus r times, it's 1 plus z over r. Actually, I'm going to write it a slightly different way. 1 plus 1 over r times z plus 1 over r squared times z squared plus dot dot dot. And then there's this b part. It's like plus b over negative s times 1 plus 1 over s z plus 1 over s squared z squared plus dot dot dot. Why did I do this? I did this because my goal was to find a nice formula for the nth coefficient of that big Taylor series. Can anyone tell me what the nth coefficient of blah 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 is? Is it nice? Does the nth coefficient have like dot dot dots in it? Or could I actually conceivably write down a formula for the nth coefficient? What's the nth coefficient? Nth coefficient means coefficient of z to the power n. It's nice, says Advait. Can anyone else see what that would be? If I have all of this, what I get is the coefficient of z to the n. What is that? Remember, on the one hand, the coefficient of z to the n is nth Fibonacci number. That's why this is exciting. That's why this generating function is awesome. It's going to be the nth Fibonacci number. But how do I read off from this thing to find out what's the coefficient of z to the power n? I see we have Brandon.
It's going to be like a over negative r to the n plus 1 plus b over negative s to the n plus 1.
Okay, I see what you did. So you did a over negative r. I'm just going to break it apart, all right? A over negative r times 1 over r to the n. Actually, I'm going to take the 1 over r and then put the n here, okay? Plus b over negative s times 1 over s to the power n. Okay, and by the way, that's supposed to be the nth Fibonacci number, okay? And this is equal to fn. Is the nth coefficient. Sorry, fn is the coefficient of z to the n. This is amazing. So that means I've just found out that for every n in the world, fn is whatever that a was, some actual legit number. A over whatever that r thing is, that's some other legit number. What does this have to do with blob math? Does this look familiar to people? This is totally like, it's blob times something to the n plus blob times something else to the n. And this is why when Chris was saying like, you know, phi and like the other thing, and that's why I said you're really close. Because actually I don't want r to the n, I want 1 over r to the n. What is 1 over r to the n? Now I need to reciprocal these things. Oh no, how do you do that? You have to reciprocal them. So let's see, will it fit here? Let's try. So if r equals this, what's my head's in the way. Let's do it on the next screen. Okay, so minus 1 plus root 5 over 2. Okay, so r is equal to minus 1 plus the root of 5 over 2. Okay, that's fine. Then what's 1 over r? 1 over r is you flip it. 2 over minus 1 plus root 5. That's not phi. Well, you rationalize the denominator. Okay, so whenever you have these radicals in the denominator, you multiply by, how you rationalize this thing? It's like 1 plus root 5, right? 1 plus root 5 over 1 plus root 5. And the reason you do this is because the denominator becomes a difference of squares. The denominator is like something minus something and then something plus something. And that's the difference of the squares. So the answer of 1 over r is just 2 times 1 plus the root of 5 over, well, the difference of squares is root 5 squared, that's 5, minus 1 squared, oh. Bam! We got our phi. This is the thing that Chris wanted. This is the root 5 plus 1 over 2, or 1 plus root 5 over 2. That's often called the phi, which is the golden ratio. That should look very familiar. That's what we had last time in this Fibonacci formula. How about the other guy? S. S was minus 1 minus the root 5 over 2. If that's the case, 1 over s is equal to 2 over minus 1 minus root 5. Okay, now we have to times by rationalizing this guy. I don't know. Help. Maybe...
-4.
Oh, say again.
-4.
-4. Yeah, I just want to know what to write. Like, what should I multiply by? Like, it was some minus word. We have to decide where to put the minus. Oh, whatever. Let's just do this. I know this will. It might be ugly. We might have put the minus in the wrong place. Okay. I'm multiplying by 1. But once I multiply by 1, then what I get on the top is twice 1 minus root 5, and the bottom gives me difference of squares, which is like, yeah, it's negative root 5 plus 1 and negative root 5 minus 1. That's what's going on here. And negative root 5 happens to square to 5. And I'm just writing it like this, just to show you what I've done. I have a difference of squares where I have negative root 5 plus or minus 1 multiplied by each other. And that is exactly twice 1 minus root 5 all over 4, which is 1 minus root 5 all over 2, which is what we had last time. That's the other thing we had last time, 1 minus root 5 over 2. So what we have just found out, if you put everything together, is we just found out that the nth coefficient is going to be some blob times this 1 plus root 5 over 2 to the power n plus some blob times 1 minus root 5 over 2 to the power n. That's what we got over there. And then you just finish the same way as before. If you remember, before we did some matrix multiplication, and when we did some matrix multiplication, we eventually got to this thing with the blob math, and we said just stick in n equals 0, stick in n equals 1, and after you stick those in, you can figure out what the blobs are. So we have just found another way to derive the entire formula for the nth Fibonacci number. Advait, do you have a question? Or a comment?
Oh no, I was just going to mention, the roots of that equation look really similar to that equation that we solved for those eigenvalues for the lambdas from the matrices.
Yeah, so this equation looks a lot like the one we solved for these like lambdas. And that's why next class what I'm going to do is I'm going to show you exactly why it's actually the same equation. But over here, to minimize the amount of times we have to twist things in our head, I just first took it into the partial fractions which we're used to, saw some ugly thing, and said, oh, I want to turn those into geometric series. Those I know how to find infinite sums for. Once you're in infinite geometric series land, then you realize that, oh, they're just going to be like blobs times powers of certain things, and those certain things are the reciprocals of the roots. Bam! And then you just get the whole thing. You might wonder, well, this was so fast. Why didn't we just do it this way last time? The reason is because there are certain things we did in this one where there are dots, and there's these like murmurs of convergence, and like, does it really work? And so I wanted to at least show you another one before, which like, yeah, that definitely really works. This thing here is like a little bit of, yeah, if it works that way, it looks right. And this is how a lot of physicists discovered a lot of good physics. And actually, it's generally right. and so that's what we're seeing here. This is a bit more analogous to if things behave well, which they probably do, then we'll be able to get some heuristic and understand, why are these the powers? Why is this the nth Fibonacci number? All right. Well, welcome to generating functions. This is what we're going to do for the next 2 weeks. That finishes.
Thank you.
Yeah.